Hello again. In today's session, we are going to continue our workshop example, and we stopped last time after we discussed the application of the constraints and restraints in our model. And the step that we are going to go through today is the last step before we conduct the actual analysis. So this step is to define and to assign the loads in our model. In our working example, we have two actually types of loads. The first one is dead load, which has a magnitude of 2 kilonewton per meter square, and this is excluding the own weight of the structure, and a live load of a magnitude 3 kilonewton per meter square. So let's see how we are going to do this in SAP. So as we mentioned, again, whenever we do something, we have two things, define and assign. So first we are going to define the loads, and then we are going to assign these loads to the structure. So let's start by defining the loads. So if you click on define, you will see that you have, if you go down here, you will see you have three things regarding to loads. So you have load pattern, you have load cases, and you have load combinations. So we are going to discuss what each of those means. So the first thing that we need to define is basically with the same sequence. First, we need to define the load pattern. Then we need to define the load case type. Then this is optional. We can define some combination between the different load patterns that we defined. So let's go and define the load pattern. So if I click on that, you will see that by default, SAP has generated a load pattern called dead. This is what SAP called it by default. And it's already listed here. And this load pattern has a type of dead. So the type of the load pattern is dead, and the name is dead as well. And you have here something called the SelfWeight Multiplier, which is set equal to 1. All right. So what does this mean? Well, the load pattern, this is where you are going to define all the different load patterns or the different load scenarios that you have in your structure or in your analyzed building. So in our case, we have a dead load, which is already has been defined. And then you need to give it a name. So you need to give the load pattern a name. You need to give it a type. So if I click on this pop down menu, you will see that you have different types. You have dead, live, quake, wind, snow, other things as well. So what does this mean? Well, the type is important to define the correct type of your load pattern, because if you are going to use other options in SAP, like designing a building, because SAP can design, actually, like if you look here, there is design a menu, so you can use SAP to design the structure after the analysis is done. So for instance, for SAP to conduct design, SAP needs to do some load combinations and to do some considerations. And for SAP to do that, SAP needs to know what load patterns are dead load, what load patterns are live load, what load patterns are wind, what are snow, and so on, in order to do the appropriate combinations based on the code or the standard that's being used. So here, that's why we select this type parameter. So this is for the type. So you give it a name, the load pattern, then you specify the type of this load pattern. And then the last thing, you need to specify something called the SelfWeight Multiplier. So what does this mean? Well, if you remember, in our structure, we have different sections for the slab, for the beams, for the columns, for the braces. And each cross section, if you remember, has some kind of shape, like eye-shaped or tube or something like that. And each one of those cross sections was assigned a material. And if you remember from session number one, session number two, when we defined the material, we assigned density to this material. So SAP, knowing the cross-section geometry for the members and knowing the material density, SAP can automatically compute the self-weight of my structure. So what I'm saying here when I say the self-weight multiplier is equal to 1, I'm telling pretty much SAP, like for this load pattern that's called dead, when you are computing the loads, automatically consider as well the self-weight of the structure. So that's why I would multiply it here by 1. Okay? So this is what self-weight multiplier means. Now dead, okay, we will leave it because in our problem we have dead load, so we'll keep this load case, load pattern, and then I will need to define another one and I will call it live load. So let's define a new one. How we do that? Well, first you modify the text, so I will call it live. The type is also live. And you will see here that once I selected live, automatically SAP set the self-weight multiplier to 0, because this is what's commonly been done. If you are using a live load, you are not going to consider the self-weight of the structure, because the self-weight is a dead load, not a live load. Okay. So now if I do that, if I click on add after I put all the values, if I click on add new load pattern, then now it goes into the list. Of course, if you make the mistake and you put the self-weight multiplier equal to 1 when you add the live load pattern, this means that any load combination, if you do any load combination that includes live load and dead load, SAP will count the self-weight twice, which is of course wrong. So that's why you need to be careful with the self-weight. So that's it. So now I define the load pattern in my structure based on the example that we are doing. But if you have other cases, you can keep defining those. So you can call this, you can make different types of live loads. So you can make live load on the roof or something, and then you can add it. So you can make different load patterns if this is needed. So that's it. I'm done here with the load pattern. So I click on OK. So here it's telling me ignore the last edit, this thing that I was just writing. So I will say yes. So now I have the two load patterns. Let me say something here quickly with regarding to the self-weight. So we set the self-weight multiplier equal to 1 for the dead load and equal to 0 in the live load. But actually, if you don't want to consider the self-weight, there is another way to do it. You can actually, if you go for a specific member, if you go to define, if you remember, if I go to the section, the frame sections, any of the sections that we have defined before, if I open it to modify, and if you click on set modifiers, you can actually set the weight modifier for a specific member or cross section to 0. So this you can do here, if for some reason you need to do that, of course. But typically we don't do it. But if you want to do for a specific member that you don't want it to be included into the self-weight computation, so you can make the self-weight multiplier over here equal to 0. So this means when SAP is going to compute the self-weight of the entire structure, it will multiply 0 by whatever the weight, and then the weight of this member that has this cross-section will be 0. Okay, This is something, again, just to revisit what we have discussed when we define the cross sections. Okay, so the self-weight multiplier, again, if I go back to the define the load pattern, for the dead load, it doesn't need, you don't need always to have the self-weight multiplier equal to 1 when you are defining dead load. Because in some cases, especially if you are designing a structure and you're doing the first iteration in your design, so when you are doing the first iteration, you put some random or approximate member sizes into your model. So you put some approximate member sizes into your model, and then you conduct the analysis, and after you conduct the analysis, you design the members, and then you assign the designed members again, and then you do another analysis. So it's kind of an iterative process. So sometimes when you are doing the first iteration, in many cases, we typically put the self-weight multiplier equal to 0 in the dead load. Why? Because at this point, we are not sure about the members or the cross-section that we assigned in our model. So instead of making SAP calculate the self-weight based on these approximate cross-sections, instead of that, I'm going to assign an equivalent self-weight for the structure, which is again approximate as well, but this is what we typically do. So the self-weight multiplier for dead load, it doesn't need to be always equal to 1. But for the worked example that we are doing here, I'm considering that the members that we are using are final or close to final. So that's why I will make SAP compute the self-weight based on those directly. Okay, so now after we define the load pattern, the next step is to define the load cases or the load case type. So what does this mean? Let me click on that. So you will see here that for every load pattern that we defined, the dead and the live, there is an equivalent load case that has been generated over here. And if I select on any one, so you will see like dead load, and next to it, it says linear static. And if I click on live load, next to it for the load case type, it says linear static. Okay. So what does this mean? Well, in this dialog, defining the load case type, we are defining the type of analysis that's going to be conducted for this load case. So what does this mean? Well, let me click on live, for instance, and let me click on modify show load case. So if you click on that, you will get this dialog box. And here you have the load case name. And on the right, you have this pop-down menu that has the load case type. And right now, static is selected. So what does static mean? Well, static, as the name tells you, well, static means that you are going to apply static loads that are not moving. So this is static analysis. It means that there are no dynamic effects. Time is not an issue. You don't have inertia forces, okay, or accelerations or something like this. So we are going to apply static load. There are other load case types that you may use. For instance, there is time history. So time history is, for instance, if you are going to apply an earthquake. So if you are going to apply an earthquake to your structure, so this is the earthquake is pretty much an acceleration time history. Okay, so you have the load is basically acceleration. That's a function of time. So this is called the time history. So this is a dynamic load case. You have other things like moving load, and this is moving load. This is something like if you are analyzing a bridge, for instance, so you will need to model a truck or something like this, so a moving load. You have multi-step static, so this is static again, but static that's being conducted into a number of steps. So for instance, if I have a structure and I want to apply to the structure 10 kilonewton of force, instead of applying the 10 kilonewton all at once, I can apply it into multiple steps, okay, but all static again. And you have many other options as well that you can again look at the manual to check what are those and in what cases do you use them. So it's static. So this is the first thing, it's static. So we understand here, static, we understand what this means. But then again, you have another thing that says linear. So this is what the two radio buttons over here. So the analysis type. Is it linear or non-linear? So what does linear means or non-linear? What does this mean, or what does it refer to? Well, in any structure analysis problem, you have two types of nonlinearity. When you do any structure analysis, okay, you have two types of nonlinearity. The first one is material nonlinearity, which is, as you expect, material nonlinearity, meaning that if you have, like, for instance, steel, so steel can be elastic if it has like small strains and deformations, so it's elastic. But if you have large deformations and so on, it can become plastic and it can yield. So this is material nonlinearity. Okay. So this is one source of nonlinearity coming from the material. The other source of nonlinearity is the one coming from the geometry. So the one coming from the material, this is covered when we define the material. If you remember, when we defined the materials, we specified Fy, like the yield stress, and we defined F ultimate, the ultimate stress, and so on. So SAP knows how the material in our case behaves in the non-linearly. And when we define the concrete, we also specified the compressive strength of the concrete as well. Now, this is for the material nonlinearity. The second part of the nonlinearity relates to the geometry. So what does this mean? Well, let me here use the whiteboard to show you something. So in this example right here, I'm showing you like a cantilever member that has a length L, and this member is being subjected to a lateral force V and an axial load P. So if I ask you, what is the moment at the base of the cantilever? So probably you would say that's very easy. It's V multiplied by L. That's it. You just take every force and you multiply it by the lever arm, okay, and then you get the moment. So here you can say easily that the moment is equal to V multiplied by L. What you have did here is correct, but what you have did so far is assuming that you don't have geometric nonlinearity. So what does this mean? Well, in reality, when you apply this V force, the cantilever is going to deform something like this. And I'm exaggerating a bit just to show you. So this means that the cantilever is going to displace by some distance delta. And again, the force P is still here. And the force V still here as well. So in this case, if I look at this second scenario and I tell you again the same question, what is the moment at the base of the cantilever. You will tell me, ah, in this case, the moment will be V again multiplied by L, the length, plus the axial load, this P, the axial load here, I'm calling it P, multiplied by this lateral displacement, which is delta. So the difference between these two cases is basically, in the first case, case number 1, we are considering linear geometry. We are not consider geometric nonlinearity. In the second one, we are considering the geometric nonlinearity, and specifically, we considering what we typically call the P delta effect. So this is called the P delta effect. So the difference between the two is that if I specify I'm using linear geometry, so this means that the equilibrium equation is being solved using the undeformed configuration of the column or of the member in general. But if I said I want to use or include geometric nonlinearity, so this means that I'm going to solve the equilibrium equation of forces, but using the deformed shape of the member. So this is just in brief the difference between geometric nonlinearity if you include it and if you exclude it. Not only that, actually, you can take it even a bit further, because you can note here that in the deformed shape, if you have the column or your member here is deformed a lot, you have very large deformation, and again I'm exaggerating over here. So you have this P again, and you have this delta, so this is the P delta we said, and you have the force V. So additional to the, so again you can say that the moment, again, the moment at the base is still M equal to V L plus P delta, but not only that, you have additional term as well, because if you have excessive deformation, the member itself, this member, is being curved, as you see here. So you have some curvature to the member. So the member itself is being deformed like this, with some deformation that we typically call it small delta. So this means that my moment will be VL plus P delta, which is what we call the global P delta, plus P small delta. So this one, we call it the member. So this one, we call it the member P delta. While this one, we call it the global. So this is the global P delta effect, and the other one we call it the local member P delta effect. So in general, if you are using some kind of analysis software, structure analysis software, you are being asked, when it comes to the geometry, are you considering nonlinearity? And then you need to say yes or no. Well, that depends if geometric nonlinearity is important in your structure or not. So if you have a structure, some kind of structure that is flexible, that will deform a lot, and that's carrying some kind of large axial loads, something like a transmission tower, for instance, or a cylinder column, like a building that has like some cylinder columns. So in this case, you are going to say, yes, I want to include geometric nonlinearity, and then the program will typically tell you which type of geometric nonlinearity do you want to include. Do you just want to include the global P delta, which typically for small deformations, or you want to include the full thing, the formulation for large deformations, the one that includes the global P delta and the local P delta. So this is in a nutshell, this is what geometric nonlinearity means. So now you know that you have two types of nonlinearity. Okay, you have the geometric nonlinearity. You have the geometric nonlinearity, and you have, which is this one, and you have the material nonlinearity. And the material nonlinearity is the one relates to, are you in the elastic behavior of the material or in the elastic behavior of the material. So if I go back to SAP, right now we are selecting linear because, well, typically we are analyzing a typical building structure that has like very small gravity loads. So maybe a linear static is the appropriate way to go. We don't need to go nonlinear. But if you want to select nonlinear, you will see that now you will have these additional options. So now SAP is telling you geometric nonlinearity. What do you want to include? If you say none, this means that geometric nonlinearity will not be included. The only thing that will be included in this case will be the material nonlinearity only. If you want to include the geometric nonlinearity, which one do you want to include? The P delta, the global one, or you want to include as well the local member P delta, which is here it's called P delta plus large displacements. So again, if you go to the SAP manual, you can read more about those. So this is a very, very important thing to know. Basically, what is nonlinearity? What are the sources of nonlinearity? These are all basic things that structure engineer should be familiar with. So what are the sources of nonlinearity? The material and the geometry, and how it's being handled in both cases. Okay. Now in this small analysis, I mean, you can select, you can say, so why not? If I want to be more accurate, why don't just select P delta plus large displacement, which is fine. We can select it. Of course, if you have a huge structure or something like that, any option that you use means that the analysis time will increase a bit more. But in our case, it's not a big model, so you can include P delta plus large displacements, that's fine. And then you click OK. So now if I do that, so now it says nonlinear static. Okay. So that's fine. I will leave it like that. I will leave the dead load as a linear static. That's okay. So when the program is computing the forces according to the dead load, it will just use linear static. For the live load, it will include the nonlinearity. That's fine. The other one that's already by default defined here by SAP, it's called model. And the load case type is model. So model analysis, if you have taken a dynamics course or like a numerical methods class, model analysis is pretty much, this is an analysis that you do in order to find the fundamental periods or frequencies of your structure. So as you know, any structure has natural frequencies at which it vibrates and deforms. So if you want to find these natural frequencies and the corresponding model shapes, so you conduct what we call a model analysis or an eigenvalue analysis. So this is by default, it's already included, so we can keep it as it is. But of course you need, well, if you are already familiar with dynamics and this type of analysis, in order to conduct a model analysis, you actually need to define the mass in your structure. So mass is different than weight. So you need to define the masses inside your structure. But since this is not the situation in our building, that the working example that we are working on, so I will leave this as it is. And if you want to read more, you can again check the CSI website. So now I click OK. So now it's done. So now I defined the load pattern and I defined the load case types. The final thing is to define the load combinations if you want to include load combinations. So right now I have those two load cases, but if I want, and if I start assigning loads, actually let's leave the load combinations to the end. Let's leave the load combinations to the end. And let's now, using those two load patterns that we defined, let's start assigning loads into our model. And then at the end, I will talk about the load combinations. So let's start by assigning the dead load, which is 2 kilonewton per meter square. So I'm going to assign this to the floors. So I'm going to select the area elements, and then I will go to the assign. I will go to area loads. So this is the second part here. So you have here joint loads, frame loads, and area loads. So I will go to area loads. And then there are different types of loads. You have gravity load, you have uniform to the shell, you have pressure, you have temperature, you have many things. So we can apply gravity because all the loads we are applying in gravity, but I'm going to select actually the general case, which is a uniform area load on the shell. So I will select this one. So here I'm going to specify the load pattern. So now I have the dead and the live, the ones that we defined. So I'm going to assign this load under the dead load pattern. The coordinate system is the global one. The load direction, you can say gravity, or I typically like to use the global axis. So I'm going to use the Z direction, which is the vertical direction. And then the load, I'm going to specify negative 2 kilonewton per meter. Because since now I said Z direction, and the Z direction, the positive is going upward, and I want to apply the load going downward, so I say negative 2. Alternatively, you can select gravity, and since this is gravity, so gravity is pointing downward anyway, so you just say 2 in this case, not negative 2. So again, this is up to you. From a personal preference, I always like to use the global axis XYZ, and then specify the sign for the load. The last thing is you can select if you want to add this new load to existing loads or to replace existing loads, because sometimes under the same load pattern, maybe after we apply those negative 2 kilonewton per meter square, maybe we want to apply something else, like maybe after this I want to apply on the roof an additional half kilonewton per meter square on the roof. So if I want to do that, then I would select add to existing. Okay, so you have to be careful with that, because if you are adding loads to the same element a second time, you have to be careful. Are you going to add those to the previous loads, or you are going to replace what you have already defined? So you have to be careful here. So in this case, it doesn't matter anyway, because I haven't defined anything else, and I'm only defining just one load. So I will keep it as it is, and I will click apply. So now already this has been updated, and it says here area uniform dead, and you see the values 0, 0, meaning that there's 0 load in the X direction, 0 load in the Y direction, and negative 2 in the Z direction. If you want to double check at any time, again, you can select, if I want to check what are the loads on this area element, you can select the area element and right click. And if you go to loads, you see over here that it says that you have assigned to this area element a uniform load in the global z direction equal to -2 kilonewton per meter square. So that's it. So now we defined this way we defined the live load. Now this is done. Let's now define the live load, which is 3 kilonewton per meter square. So we are going to do the same thing. So I'm going to select the area elements again. I can use the previous selection. Oh, because we only selected one. So okay, let me select again the area elements. And now I will go to assign again, area loads, uniform shell. And this time I'm going to select live load in the global z direction, and this will be -3 kilonewton per meter square. Replace, yeah, that's fine. You can replace because this will be under live load pattern. So you are replacing things. You see, if I hover here, it says replaces area uniform loads that are assigned to the specified load pattern. So it will not replace what we already did in the dead load. Under dead load, it will only replace anything that we may have defined under live load. So I will click apply, and that's it. So that's it. So now we defined all the loads actually in our example, okay, which are both of them are uniform area loads, but there are other loads that you can typically specify. So you have point loads. So for point loads, I'm now showing you just for illustration. It's not part of the workshop example, but I'm showing you just for illustration. So let's say that I want to apply some kind of load on this point. So you select the point, you click on assign, you go to joint load, and then you go to forces. And then again, you specify the load pattern. You specify the force, so you can apply forces or moment at this point. So for instance, you can say apply in the y direction. I don't know if you have like something like wind load, so maybe you are going to apply something in the y direction, let's say 5 kilonewton. Okay, and if you click apply, so now you see here 5 kilonewton. If I select the point again, and let's say like make it -5 and say apply replace, so now you see the value here, 5 kilonewton that has been assigned to this point. Okay, now let me put it back equal to 0. Okay, and say okay. Sorry, so let me select because I want to remove it. So I go to joint loads, forces, so 0, and I click apply, and while replacing. So if I do that, so now this load has been removed. So this is for point loads. If you want to apply some line load, uniform line load, some kind of line load on the members, so you just select the member, you go to assign, frame loads. Again, you have the same things that we discussed in the area loads, you have them here. So if you go to distributed, again, you need to specify the load pattern, the coordinate system, the direction. So let's say Z direction again. Okay. The load type, well, it's force. Let's say it's force. The uniform load, kilonewton meter, let's say -1, for instance. Okay. -1, this is if I'm applying a uniform load along the member length. So you can specify here. If you want to apply some kind of trapezoidal or like rectangular type of load on the element, then you can actually come here and specify the load value or magnitude with respect to the relative distance from the end, or you can specify it with respect to the absolute distance from the end. Well, it's up to you. You can have the two options. But this is if you want to apply some kind of irregular or trapezoidal loads. So let's say that we are applying just a uniform load, typical uniform load. If I click apply, so now you see here a uniform load has been applied in the global Z direction pointing downward. Okay. Let me select it again and let me put 0 and let's say apply just to remove it. Okay. One more thing when it comes to loads, you have noticed here that you have X, Y, Z, and you have what we call X projected, Y projected, and Z projected. So what does this mean? Let me open the whiteboard again. Let me clear this canvas. So what does this mean? Well, if you have like some kind of, let's say, a frame element that looks something like this, that's inclined. Okay, so this is a frame element that it's inclined by some kind of angle theta. Okay, and you have the direction like this is axis X and this is axis Z. So if you are applying load to this member, if you say in the global Z direction I'm applying -1, so this means that the load is going to be applied on the inclined length. So if this is the uniform total that you're applying, this will be applied on the total length of your member. If you, however, select Z projected, so this means that the load will be applied on the projected length, which is the horizontal length in this case. So in case number 1, W will be, if you want to translate this W into a single force, it will be W multiplied by L, where L is the total length of the member. But in the other case, it will be W multiplied by L, L cosine theta. Okay, so this is the difference between projected and regular axis when you are applying loads. Okay, so this covers it. You can apply some concentrated loads on the frame elements. So again, if you select the frame element and you go to assign and you go to frame loads and you go to and you go to point. So here again you specify the load pattern, the coordinate system, the direction, the load type, force or moment, and then you can say, okay, at a distance of, like let's say at half distance, apply -1 kilonewton, and at 3/4 of the distance apply, I don't know, 5 kilonewton upward. So if I click apply, so now you see you can apply some kind of concentrated loads like this. So this is instead of actually creating nodes on the members and then applying like point loads, this is a much easier way to do it. So let me select again and let me put here 0 and replace the existing loads and click apply. So now okay, it's removed. So now we have went through all the types of loads that we typically use, like area loads, point loads, and frame loads. The last thing so now everything is done. The next thing is pretty much to start doing the analysis. But before we do that, we can actually define load combinations if we need to do that. So if you click on load combinations, so by default, SAP didn't define any load combinations, which makes sense because by default, SAP had already created one load case, which was the dead load case. and you cannot make load combination from just one load case. But now, since we have the dead load and the live load, we can start adding or creating a load combination. Okay, so now let's define a new combination. So I'll click on add new combo, and we need to give it some kind of name. So by default it's called combo 1. That's fine, I can leave it as it is, or you can name it something else, it's up to you. So in this one, let's use the default load combination. Like, let me use the dead load, and I will multiply the dead load by 1.35, and then I will add the live load and multiply it by 1.5. So that's it. So this is done. Now this is the load combination called combo 1. The program will take the forces and stresses and moments, everything that's coming from the dead load, multiplied by 1.35, and add to it whatever the program is getting from the live load, multiplied by 1.5. The type of addition, we are just doing a linear addition. There are other ways to do the combination. There is like envelope, there is absolute addition, so we don't care about the sign. So if you have a negative moment and a positive moment, I don't care, just add the absolute value of both. Okay. Envelope, just don't show me whatever you get from each case, just show me the envelope, the maximum from both. Okay. So these are all different types of combination that you can consider. Okay. So here I will keep for this linear addition, and I will click OK. So now I have it done. Okay. Let's actually make another load case and make another load combination. So if I go back to define, if I go back to load pattern, let me make another load case, and I will call it live half. Add new pattern. Okay. So in this one, live half, in this one I will just put live load on half of my building. Okay, just on half of my building. So this is just to demonstrate some things when it comes to load combinations. So I will go to assign, I will go to area loads, I will go to uniform, global Z -3, not live, the load pattern under live half, and say apply, and then OK. To make sure that everything is correct, you can right click on the area element, go under loads. So now this area element has -2 for dead load, -3 in live load, and a -3 for the other live half, and I say OK. And then again, if I go to the load combination again, I can make another combo. I can say it combo 2, that's fine, which would be the dead load 1.35, add, and again the live half in this case multiplied by 1.5, add. So now I have this one like this, and I can say OK. So this is what we typically do. You try to make different combinations of all the different possible combinations or scenarios, loading scenarios in your building. So one scenario that I can have dead load, well, the dead load will always be there, so it has to be in all of the combinations. One case I have the dead load, and then I have live load everywhere. And the other combination is I have dead load and I have live load only on half of the building. Okay. And then when you do the analysis, you can check the forces and things that are coming from each load combination. Okay, so now that you have the two combinations, so once you run the analysis, and then let's say that you are looking at this corner column, for instance. So you can go to combination number 1, and combination number 1 will tell you that the force, the axial force, for instance, in this column is 10 kilonewton. Okay, and if you go to combination number 2, you will find that the force is 15 kilonewton. And then, based on this, you will say, okay, 15 is the larger value, so I'm going to design my member using 15 kilonewton, which is fine. But of course, if you have a big structure and you have many members, this will take lots of time and it will be tedious to go through each element and look at the different combinations and see which value is the largest. If you are doing this manually, it will take time, especially if you have many combinations. Like in this case, we have only 2 combinations, but in reality, you may have 15 combinations in an actual structure. You would have like 15 different combinations. Okay. So what you need to do, you can make, instead of doing this manually yourself, you can have SAP do this for you. So you can make a new combo, and combo 3, okay, we can call it actually like combination envelope, because I care about the maximum value, okay. So I can call it combination envelope, and this one I'm not going to add the dead or the live or the half-live or whatever. I'm going to add these 2 combinations that I made. So combination number 1 and combination number 2. Just not add them, just getting not linear addition. I'm going to get the envelope of these 2 cases. So this means that this combination will give me the envelope of the forces from this case multiplied by 1 and this load case multiplied by 1. Now, of course, the load case in this situation is an actual combination by itself. Okay, so this is how you do it. So that's it. And then if I look at the combination envelope, then I see the maximum forces or stresses or whatever, or moments that I need to design for. But if I want to look at the specific cases, then I can look at the moment diagram, shear force diagram for a specific load combination. All right. So that's it. I will click OK. So now I have those 2, combination 1, combination 2, and combination envelope, and I have, of course, the individual load cases. Okay, that's it. So that's all for the definition of loads. We are done with the definition of loads. So next time we are going to go through pretty much the last thing, which is defining the analysis type and conducting the actual analysis and visualize the results. Okay, so thank you for your attention and see you in the next session.